name is Alejandro Mendoza, and I will be presenting Team 38's DP3 presentation on our product, the Lofted Bedside Pulley. You can see our logo to the right and what we call ourselves as Pulley Innovation. Now, when we were deciding on what product to produce for our semester project, we wanted to consider the customer, because to us, customer happiness is a key founding idea of our project. So, in order to do this, we created the customer profile. How we did this was just taking our average college student and analyzing what we could do to make their life easier. Now, when we were looking at this concept, we landed on the idea of the college dorm craze. You know, when freshmen are excited to be, usually for their first time living on their own, they want to make their dorm room all cute and have cool gadgets. And that led us to our idea of the lofted bedside pulley, because college students often loft their beds so they can put their desk under so they have more room in their dorm. So, with our emphasis on affordability, that leads us to our mission statement, which is to create an affordable bedside pulley to make college dorms a little more unique and student lives a little more easier. Now, with our product idea, we then needed to gather what customers thought about this. And so what we did was we surveyed the population group, which was people who lived on campus housing, and gathered their thoughts, and that summated in the customer needs or interpreted needs, with the most important ones being the weight and the appearance, because they want to make their dorm room look cute, and the affordability. Now, what we needed these needs for was to make a use case, which was how our team, thought the customer would use our product. And what we figured was it would be a simple input-operated pulley that lifted a transport medium from the ground or from the desk to the lofted bed. Now, taking the previous slide further, you can see how we simplified and separated the process of pulling the pulley into actual steps. We have the input, which is electrical or manual energy, feed it in to either the pulley or with the electric version, an electric route to transfer the pulley, and how the pulley lifts the transport medium to bring the consumer his items. Now, this diagram above is the super simplified, really basic version of what the flow is for our product to operate. You have energy coming in with the products coming in, energy coming out with the products coming out. Now, after all the previous was considered, we started with generating concepts using a concept combination table, which you can see right here in this blue titled table. All these lines represent different ways our products could have gone. What we did was we picked the best product out of combining all these great ideas and worked on one individually to see, what's the best one we can come up with. So after that was done, we received some feedback from our peers, which was absolutely positive. And considering that went great, we then decided the process of concept selection. What we ended up doing was combining two of our team members' products to create one superior product. And what that's made it to was a manually operated hand crank pulley that attached to the lofted bedside guardrail via C-clamp, and then it had a bucket as a transport medium. Now, this was decided using the criteria of cost, which was set forth in the rubric, to create an actual prototype, and team member capabilities, and practicality. Now, sort of in parallel with this, we needed to look at the intellectual property of others to see if we actually had, the rights to create this product or the ability to obtain them. And that means paying someone else to use their patents. Speaking of patents that were integral to our products, such as the pulley and the C-clamp, which are the two numbers you see in the screen box, those need to be checked, or because you don't want to face a lawsuit. It's not fair for someone else to create an idea and you just produce a product. So, luckily for our team, all the parts needed for our product have been long past their expiration dates because, bullets have been around since medieval ages, and I think the formerly US patent expired in 1800s. So, good for us. Now, with a fully realized product, we started the failure modes effect analysis, which is basically considering what can go wrong and where, and how it might bring harm to our customers. Now, that you can see the results of our in the table to the left. And what we noticed immediately about the table was the most common potential cause of failure, which is overloading our product. If you put too much weight on the transport medium, it can cause our product to fail in multiple places, which is really bad. Now, this is easily calculated, like we can easily see what the max weight limit is through a simple deforms and status calculations. The trouble part for us is making sure the customer realizes how much weight they can put on this. Now, this can be solved by clearly explaining and defining a set weight limit for our product in such a way that there's no room for the customer to interpret, maybe I can go over. No, it's a set limit. This is the max you can put on there. And this is for their own safety, of course. Now, the next biggest noticeable thing was the amount defective production of our products can affect. Like, we're not blaming if our product fails that the production of a part was defective. We're just saying that it could happen. Now, it is going to be corrected by quality assurance, so that fixes that. Now, our team then began to put together a, figured cost for one prototype. You can see on this table to the left here, our design for manufacturing. We used Proto Labs with their injection molding website to figure out the cost for one prototype of our product. Now, you might be wondering, why is the so high, $3,200? There's no way you can make a profit off that. And you'd be right, because injection molding is not practical for making one or a small number of products. The bulk of the price is caused by the mold, so after the mold is created, each product therefore after should be cheaper. So this would be used in a mass production scenario and not for our single product. To the right is our design for assembly. In a factory setting, we simplified down the assembly of our product to 6 parts. And when calculating the time it takes to produce, we took in factors such as maneuverability, angles of orientation, and size. And so we come up with 38 seconds to produce each product. The cost of assembly, $15 an hour, which is, we think, a reasonable wage. That leads us to each product costing 16 cents to assemble. Now here you can see our bill of materials for one product prototype. Like I explained before, it's very high because injection molding is not feasible for one prototype. Almost $3,000. Here are our final designs. What I didn't tell you before was that in the concept generation process, we were creating CAD models for the major ideas. And then we ended up on this final model right here for our final product. And now you can see our prototype on the right side, but that prototype has a $60 budget, very far from $3,200. And instead of a lofted dorm bed, we are using a door as the C-clamp to attach to. We figured this was okay considering they are the same width. Now, this all ends in what we think we could have done better. We'd have absolutely liked to have electronic version, because electronic version is better, a button to simply pull it up. That would have, customers stated that they wanted that. Unfortunately, it is very expensive and not within our $60 budget minimum or limit to create, and our team members lack the ability to create a fully rigged electronic version. What we would like to improve, in like in a 2.0 product, is maybe detachable mediums, like a bucket can be switched out with a tray, or a tray with a platform. That would be very cool. That is our DP3 presentation. Thank you for your time.